All right, we're back again with section 6.3, doing hypothesis tests for match pairs. And just thought I'd run through another example in which we have data sets given to us. So, you wish to test the following claim at a significance level of alpha equals 0.005 or 5 thousandths. For the context of this problem, we have the mean of the differences of the population is mu sub 2 minus mu sub 1. The first data set represents a pretest and the second data set a post-test. Our null hypothesis is that there is no difference. The difference equals 0. And the alternate hypothesis is that the difference is going to be greater than 0. So we are dealing with a right-tailed test. So, you believe the population difference scores normally distributed. We have the data set here. I'm going to just grab this data set. And I'll put it here, paste. Again, I like to use special every once in a while. Excel does something funky where a number comes through as not a number. Now, when we're talking about the differences, we really want to know the post-test minus the pretest. So in this case, we have the post-test, and we need to subtract the pretest. And then here, let's just fill it all the way down. And I should have probably just left that alone here. N is equal to 15. Some good stuff to know. So N here is 15, which means the degrees of freedom is going to be 1 minus that. Actually, 1 less than that. Ignore what I said the first time. We'll take the degrees of freedom is 1 less than our sample size. So now we need x bar sub d, which is the mean of those differences. And if we're interested in a mean, Excel calls it the average. Snag our whole data set here. And I don't know if it's actually exactly 1.52 or if that number goes on and on and on again. So as you're working through the data, you might want to just click on the cell. So the sample standard deviation of those differences, S sub d, is the standard deviation of the sample. Grab our data set. And we're sort of learning what it is that we need to know in order to get to our test statistic, which I think is the first answer here. To find a test statistic, we need to know what the standard error is. The standard error is the standard deviation of the differences divided by the square root of our sample size. And I'm moving a bit quickly here in that we've done a lot of these steps many times before, but you can always slow it down or speed it up as needed. So our test statistic, which I forgot to write the test stat here, easy. Oftentimes it was the difference of these, but with these ones, this is the mean of the differences. So I just take this one and divide by our standard error, and we've got this. Now, this was a right-tailed test, and so if I was drawing a picture here, once I have my test statistic, and you can kind of figure this out. I mean, you don't have to really wait this long. I just kind of like to figure out how to place it sort of reasonably. When I know these differences are mostly positive, or I've calculated this guy and it's positive, it's going to give me a positive test statistic. So somewhere over here is my 0.76, and I don't really know that for sure. I'm just kind of guessing. And I'm also approximating here. But I know I'm looking for the right tail there. And again, I kind of stepped away from using the stylus so that it might be a little bit more like something you can do. Now going old school, connecting back to what we used to do, we can do a t-dist, 1 minus because we're looking for the right side. This function always finds the area to the left. Put in the test statistic, comma, degrees of freedom, and true. Now here we have a p-value, and we would round it to 4 decimal places. Now again, if we want to be fancy, the t-distribution has this fancy t-distribution right tail. Click on our test statistic, comma, degrees of freedom, and just pops it right out for us. So I kind of like the first one a little bit more because it connects to what we've been doing a little bit better, but not a big problem no matter how you like to solve this one. So our test statistic to 3 decimal places, we've got a 7, 6, and an 8 followed by a 1. so 0.768. And the p-value, 4 decimal places, we have a 2, 2, and a 7, followed by a 5, and then a 7. So the 5 is going to round up to 6. Comparing our p-value to our alpha here, our p-value is greater than our alpha, and so we fail to reject the null hypothesis. And we got another one correct. So I think I'm going to stop here with examples. So this is the last one, another one with the data set, and I think we've done one that's two-tailed, one left-tailed, one right-tailed. So you have kind of the variety there. You just need to add in a bit more of the context.